Welcome to The Explainer. Today, we're uncovering the invisible physical rules that literally keep absolutely everything in our world exactly where it belongs. I mean, have you ever wondered why massive skyscrapers don't just tip over in the wind? Or how your body seamlessly keeps you from face planting every single time you take a step? Well, it all comes down to the hidden architecture of balance. Basically, the laws of statics and torque. Get ready, because we're about to completely change how you look at the physical world around you.
Here is our roadmap for today. We'll start with the secrets of balance, then move into the rules of static equilibrium, torque and the lever law, and the biomechanics of the body. Finally, we'll tackle the classic ladder problem and end with what I like to call the pivot cheat code. Okay, let's dive into this first section, the secrets of balance. I want to kick things off with a kind of funny, but actually really revealing question. Why are chickens fundamentally better at balancing than humans? Seriously, think about it for a second. When was the last time you saw a chicken just accidentally trip and fall over? Probably never, right? Well, the answer is all about the center of gravity. For us human adults, our center of gravity is actually pretty high up. It's sitting right above our hip joints, and it rests over a fairly narrow base of support, our feet. Because our feet aren't exactly huge, any little forward or backward bump makes us pretty unstable. We actually rely on a constantly working nervous system and tiny muscle twitches just to stand completely still. It's also why babies have such a tough time learning to walk. Their center of gravity is incredibly high, like right up between their shoulders. But a chicken's center of gravity is way down below its hip joints, nestled right between widely separated, really broad feet. Its body essentially acts like a pendulum just hanging between its hips. So even if a chicken gets a pretty big bump, the restoring forces naturally bring it right back to perfect equilibrium with almost zero effort. Section 2. Rules of static equilibrium. Now, it's one thing for a system to be balanced, but is it actually stable? You see, there are three distinct types of equilibrium. First up is stable equilibrium. Think of a marble resting at the bottom of a cereal bowl. If you nudge it, it feels this restoring force that pushes it right back down to the center. Next, we have unstable equilibrium. That's like a ball perfectly balanced on the very peak of a steep hill. If it gets displaced even a tiny bit, it experiences a net force in the exact same direction as the displacement. It just accelerates rapidly away from its starting point. It's gone. Finally, there's neutral equilibrium. Picture that same marble, but now sitting on a perfectly flat table. If you move it over a few inches, it just happily stays in its new spot. The equilibrium is totally independent of where you move it. So for an extended rigid body, say a bridge, a skyscraper, or even one of your bones, to be in a true state of static equilibrium, it has to meet two strict mathematical conditions. Condition 1, the vector sum of all forces acting on the body must be exactly zero. That means no translational motion at all. It's not sliding up, down, left, or right. Condition 2, the vector sum of all torques about any axis must also equal zero, meaning absolutely no rotation, no twisting. If both of those are perfectly zero, your structure is officially safe, static, and not going anywhere. Section 3, torque and lever law. We just mentioned torque, which is basically the rotational equivalent of linear force. And the absolute best way to wrap your head around torque is through the lever law. Imagine a rigid beam balanced perfectly on a pivot. It won't rotate as long as the torques on both sides are completely equal. You calculate torque by taking the magnitude of the applied force and multiplying it by the moment arm. And the moment arm is just the perpendicular distance from the pivot point right to where that force is applied. So what's the big takeaway here? The longer your moment arm, the less actual force you need to use to get the exact same rotating power. Now, what's really interesting about this is how it applies to a super frustrating real-world scenario, trying to loosen a stuck lug nut on a flat tire. With a standard L-shaped tire iron, if you push down on it, the absolute max force you can apply is basically your own body weight. For an average person, that might generate maybe 500 Newton meters of torque. If you get frustrated and try yanking up on it with both hands for more leverage, you're risking a massive, unbalanced vertical force that could literally lift your 2,000-pound car straight off its unstable jack. That is a terrible idea. But look at the four-way cross-wrench. By grabbing opposite sides, pushing down on one arm while pulling up on the other, you're applying perfectly symmetric forces. This creates what's called a couple. You're effectively doubling your torque to a massive 1,000 Newton meters, but without exerting any net vertical force on the car itself. You get maximum rotational power, and you perfectly satisfy that first law of static equilibrium. Section 4, biomechanics of the body. What's really wild is that these exact same torque mechanics govern everything inside of us, right down to our bones and joints. Let's look at the human foot and ankle. When you stand up on the ball of your foot, your ankle joint actually acts as the pivot point. You've got the normal force from the floor pushing up on the ball of your foot at a specific distance, that's your moment arm, which creates a torque trying to rotate your foot upwards. So, to maintain static equilibrium and keep you from collapsing, the tension in your Achilles tendon at the back of your heel has to pull upward, creating an equal and opposite counter torque. The physics get even more intense when we move up to the arm. Imagine you're holding a heavy ball in your hand. You have the downward force of gravity pulling on the ball, plus gravity pulling down on the actual mass of your forearm. Both forces are trying their absolute hardest to rotate your arm clockwise right around your elbow pivot. To stop your arm from just dropping, an internal tendon attached to your bicep has to exert a really massive upward force. When we zoom right in on that elbow pivot, you can see exactly where that upward tendon force is applied. Notice that tiny little moment arm labeled D? Because the tendon attaches incredibly close to the actual elbow joint, that distance is super small. And hey, remember the lever law we just talked about? A tiny moment arm means you need a vastly larger force to create enough torque. This literally means the tension inside your own tendons has to be phenomenally high. We're talking many times the actual weight of the object you're holding just to keep your arm perfectly static. Pretty amazing, right?
Section 5, the classic ladder problem. Now for a legendary engineering scenario, the ladder leaning against a wall. Just think about the sheer number of conflicting vectors happening here. Gravity is pulling the ladder and whoever is standing on it straight down. The floor is pushing back up with a normal force, but the top of the ladder is also resting against the wall, which is pushing outwards horizontally. So why doesn't the ladder just slide completely out from under you? It's all thanks to the horizontal friction force from the floor pushing right back toward the wall. It becomes this really complex, interconnected web of unknown variables, and honestly, trying to solve for all these forces simultaneously can look incredibly intimidating. Section 6, the pivot cheat code. But we have a secret weapon. It's called choosing your optimal rotation axis. Think back to that second rule of equilibrium. The sum of torques about any point in a static body must be zero. Literally any point. So the crucial point is this. If you strategically place your imaginary pivot point exactly where an unknown, messy force is acting on the body, the distance from that force to the pivot becomes exactly zero. And since torque equals force multiplied by distance, a distance of zero instantly turns that entire unknown torque to zero. It just vanishes completely from your math. It's brilliant. So here is your official step-by-step mathematical cheat code. Step 1, identify the system and meticulously draw a free body diagram mapping out every single force vector. Step 2, aggressively pick your pivot point. Look at your drawing, find the exact spot where the most unknown forces intersect, and just declare that spot as your pivot. Boom, their torques are completely eliminated. Step 3, simply apply your horizontal, vertical, and rotational equations to whatever is left over. By smartly choosing where you compute your torque, you can literally turn a nightmare algebra problem into a totally simple, solvable equation. To wrap up today's explainer, I have a fun physical challenge for you to test everything we've just talked about. I want you to stand up straight so that your heels, your backside, and your back are all touching totally flat against a wall. Now, without bending your knees, try to bend forward from the waist and touch your toes. Spoiler alert, you are absolutely going to fall forward. But why? Well, as your upper body leans out, your center of gravity moves forward. Normally, your hips would naturally shift backward to act like a counterweight, keeping your center of gravity safely over your feet. But with that wall blocking your hips, your center of gravity moves completely past your base of support. Your stabilizing moment arm disappears, your net torque shifts, and gravity totally wins. Physics is pretty unforgiving, but when you finally understand the invisible architecture of statics and torque, it is absolutely beautiful. Try the wall experiment, try not to break anything on your way down, and keep looking for the balance in your world.